everybody hear me? Cool. Yeah, it's been a great honor to be invited as keynote. My name is Chao. I lead the data science team at LucyWorks. So basically, LucyWorks is a search and text analytics software company. And then we're bringing more and more deep learning stuff in our software. So today I'd like to talk about deep learning. As we all know, deep learning in the past few years has attracted a lot of attention and being disruptive to conventional machine learning. But the methods and then techniques are totally different from traditional methods. What's the connections and differences? What's the advantage and difficulties? So today I'd like to take this opportunity to do some algorithm comparison of deep learning method versus traditional machine learning, and pair with 3 different case studies in the areas of sentiment analysis, question and answering system, and healthcare image classification. Okay, let's get started. So the closest relative of deep neural network is, of course, the traditional neural network. Deep neural network is a type of neural network, but at the surface level, a traditional neural network like this in the bottom usually only have up to a few layers. But if you look at the current deep neural network, so I'd like to start with the convolutional neural network, which is where the deep learning started. So a deep convolutional neural network can range the hidden layers increase from a few to a dozen, and some of the residual network can even have 30 to 50 hidden layers. So, but problem arose when you increase the number of layers. Suppose we use fully connected layer and then make it 30 such layers, and you'll find you have a memory explosion to train so many parameters, and then the gradient cannot pass through so many layers. So architecturally, the deep learning researcher making some changes started utilizing convolution layers. So in convolution layers, the later layers only connected to a small region of the input neurons. And then it's kind of do summarization. And after convolutional layers, people use maps pooling to provide more condensed feature map. On the algorithm side, in conventional neural networks, you can see the learning rate decrease throughout the layers, which means the later layer don't have a big enough gradient to learn if you keep doing the propagation. So on the algorithm side, in addition to the traditional SEG and backpropagation, people do some changes. For example, they replace some of the activation function from sigma and tangent to ReLU to deal with this kind of gradient vanishing problem. Also, one problem with ReLU is like the output of ReLU don't have an upper limit. Then it will introduce another problem called blowing out. So another technique called batch normalization become popular. And you can see when we have a lot of layers, there will be tons of exponentially many trainable parameters. Then it's easily to overfit. So another relatively new technique called dropout is introduced. As we can see, we have to use all these type of techniques to make deep neural network work. So then why bother to deal with this trouble to make a neural network deep? What's the benefit there? There are a few famous theory. One of them is like the ability to learn hierarchies of concepts and building up multiple layers of abstraction. This is also the way a lot of real-world data is constructed, especially for image and text. For example, the picture on the first part shows how a CNN network can find the features of a picture. And then if we do some activation to see the activation at each layer, you can find that the lower layers, for example, the first convolution layer can detect edge and blob. Then the later layer detect a combination of edge and blob become texture, then objects parts, and last can, based on the object class, do the prediction. And similarly, if we apply a one-dimensional convolution network to the text data, then we can try different window size for the filter, basically find different n-grams, like 3 grams, 2 grams, 5 grams. And then basically you're trying to find the phrases. Then at higher layer, combine the phrases at the sentence level, then at the paragraph level, at document level and in the end do the prediction. And also it's becoming more and more popular. People don't apply the network directly on the word level. They go to a lower level at the character level. So if you apply a CNN at a character level, you'll find like the first layer, people can detect some word suffixes like morphology or spaces. And at the later level, can find word roots, basically part of speech information, such as detecting its articles or pronouns. Then later combine into words. And then since it's at the character level, you can do some kind of combination. Then in addition to words, it can combine to finding common misspellings, also hyphenations and concatenations. Then we go to the word level, phrase level, sentence level. So the second benefit is it has been shown like a deep network can be able to compute any kind of complex functions. So this is an analogy, analogy we quoted from Michael Nielsen's neural net and deep learning book. So he used the example, suppose you're given a task to design a computer from scratch, and then you're only given a limited number of circuits. And you'll find it's really hard to do much with shallow layers of circuits because we find even simple calculation tasks need multiple layers of assembly. So when you have multiple layers, it's easier to do all kinds of complicated computation. So the third one people always talking about is like you don't need to do much manual feature engineering in a deep neural network. For example, in the traditional computer vision, people have to use this kind of fixed value mask and then apply it to the original picture, and then each mask can detect different kind of features. For example, this mask, because it's like have positive value on the left and negative on the right, and then you apply it and do a summary, and then you will find detect vertical edges. But in order to do a complicated task, for example, to do face detection, the traditional computer vision have to apply a series of predefined filters to classify a face, which means you have to manually construct these features, and maybe some of the features is not needed in the model. But in a convolutional network, those shared weights and biases, basically the convolutional filterings, are computed within the network through the training. So personally, I think is signal's gone. So personally, I think one of the most important benefit of a deep neural network is not just no manual feature engineering is needed. It's actually the feature generation, optimization, and evaluation was built within the same network. Because a lot of times, based on my experience, it's very important to find the right combinations of feature and then your classification or clustering method. For example, we're trying to do some tensor clustering at LucidWorks, and I find like a TF-IDF usually works well with hierarchical clustering, but not well with k-means because k-means cannot deal with outlier. So it's not about not just about which classification method you use, it's about the right combination. But if we try to fit everything together and then train the network so that I can find the sweet spots and the right combination, it's more likely it can provide superior results. And last but not least, the neural network architecture itself is pretty flexible. When we make it deep, we have more room to make all kinds of changes at different places. It's just like a Lego, and then you can do all kinds of combination. For example, currently a state-of-the-art name entity recognition method is using CNN on the front to detect character level and word level features, then feed into LSATM, basically a type of RNN, to learn the information throughout the whole sequence. So you can combine different kind of architecture at different places. Also, you can put multiple output to predict more than one thing. And it has been shown like a certain task, the prediction accuracy of a subnetwork in one output can beat a single task learning network. Also, if you can find essential features from the input by building the embedding to predict multiple things well, that means when you extract the embedding layer out, and the embedding layer is pretty representative, and you can use those layers to do other things. That's basically the fundamental idea of the Google sentence encoder, which is published last year. Okay, after seeing the benefits of deep network, the deep learning researchers is trying to make a deep neural network trainable by applying different techniques. But if you see it, you can see many techniques are directly borrowed from traditional machine learning. As I mentioned, the convolutional filtering is invented in traditional computer vision. And then in traditional computer vision, people use all kinds of pooling methods, and max pooling is just one of them. For example, they use those pooling methods in spatial pyramid matching for image compression purposes. Also, the regularization methods, L1, L2 norm is a regulation was used in deep learning, but it's pretty popular in ridge regression, lasso, and ElasticNet. And data augmentation was frequently used in traditional computer vision too. Also, there's a technique in deep learning called noise injection. You can inject the noise to the weights. Then it's basically a stochastic implementation of Bayesian inference. Then if you inject over the outputs, this method has been used since the 1980s too. In traditional machine learning, we usually plot the charts of training and validation data of the ROC curve and see the gap. And then also in Bayesian, we monitor the parameter convergence. And then early stopping in deep learning is basically a programmatic implementation of such method and then embedded in the neural network itself. On the implementation side, SGD and backpropagation is being used in traditional neural network. And then the most popular cost function is still cross entropy and MSE. And tuning learning rate is pretty essential in traditional neural network too. And then as I mentioned in the first slide, there are a few relatively new techniques such as dropout, ReLU, and batch normalization. But if we look into those ideas, none of them are totally new. So if you look at dropout was invented in 2014. So what it does is randomly removing the hidden layers by randomly applying a zero mask at different iterations. And then it's kind of equivalent to bagging with bootstrapping training data. So if we're talking about bagging by randomly destruct features and bootstrap inputs, and the first thing come to your mind, it can be random forest. So they are both doing bootstrapping on data points and bagging on features, and then also following the same principle, that is a group of weak learners can come together to form a stronger learner. But the differences here is like what random forests do is to destruct the input data. But dropout do is destruct the hidden layers, which means destroy the extracted features. So it still allows the network to learn the whole input distribution. Another difference is like a random forest is doing the bagging and bootstrapping literally. It's random sample input data and then train a model, each model, and make them convergence and then ensemble later at the last step. But dropout is doing this masking at random at each iteration. So everything is done in the same network in the whole training process. So it's a kind of approximation to doing exponentially many neural networks. So it's a relatively clever method to use. And let's look at ReLU. People starting to looking for a new activation function because when we do a deep neural network, the gradient will decrease over the layers. So if we look at the traditional activation function, for example, this is the activation function called sigmoid. It has a range of from 0 to 1. So it has a squashing effect. So if you do this activation function, your gradient will become smaller and smaller over the layers. That's why people change it from ReLU to single to ReLU. So this is the function of ReLU. So it's basically a max 0 and x, and then it don't have an upper limit on the right side. So it can reduce the gradient vanishing problem, improving convergence. And it still, since it's a nonlinear function, so it can still introduce nonlinearity. It's also faster to compute. But if you look at this function, this is nothing but a hinge function. And the hinge function has been used for a long time. And then one of my favorite traditional machine learning methods is called MARS, multivariate adaptive regression spline. And MARS is basically using a pair of hinge functions to track the nonlinear relationship between variables. And it's a pretty good algorithm, can capture nonlinearity, also provide a relatively higher accuracy than this regression. Actually, this hinge function has appeared, as I said, a long time ago. The reason the traditional neural network researcher didn't use it because you can see there's no upper limit of this function. And then it will have some blowing up problem, which means the output layer, when you don't have an upper limit, it will provide all kinds of, generate all kinds of ill-conditioned mathematics issues. So that's why people have to introduce another method called batch normalization to deal with this blowing up problem. So what batch normalization do is like, in a deep neural network, we do pre-processing, basically normalized to zero mean and unit variance at every layer of neural network for every mini batch. The benefits, as I said, is like first invented to deal with the blow-up problem. Also, it can provide easier weight initialization and learning rate setup if we use it. But normalization is such a common technique to use in machine learning. For example, in traditional neural network, the learning rate depends on your input value. A smaller input will typically require a larger weight. So if we do the standardization, then we can just use one single learning rate to train a model. It's easier to set up. Also, in a lot of machine learning methods, such as clustering regression or SVM, normalization is usually suggested too, because it can make sure variables with a larger value won't overpower the variables with a smaller value. Also, normalization across batches was used in machine learning to solve a problem called covariance shift, especially in some econometrics regression problem, because the distribution of variables can be different between training and testing when market conditions change when you do the backtesting. So if we reskew it throughout different time, then we can make sure the training and testing data are comparable. Okay, after comparing the algorithm, let's see the comparison of deep learning versus machine learning in a few case studies. The first case study I like to talk about is a question answering system for insurance inquiries. This is the project we did at LucyWorks. So we got a data set called Insurance QA online. It's basically a 20K question and answer pairs generated from historical frequently asked questions or support ticket record in insurance domain. And the goal is to build a question answering system to directly recommend answers from this existing FAQ pool or find similar questions asked before. Then the business impact is like if we put this question answering system engine on a help page or contact us page, then people can directly find the answers. Then it can largely reduce the call center workload. Also, it can facilitate the call center support team because people can directly refer to or solve the problem before. The experiment we did here, we compare a deep learning model versus XGBoost model, is basically a gradient boosting tree, versus unsupervised word embedding. So as you can see, the traditional machine learning in XGBoost model, we have to manually build a set of NLP features. The typical one is like a cosine score between TF-IDF vector of the original question and answer, or the question and answer after extracting only nouns or verbs. and I extract the question keywords, the part of speech tag, NER tag. Also, we find one particular variable is specifically important. It's like we apply a mutual information to extract the question answer and keywords association pairs. So this is one of the important variable. Also, we add the word-to-vec embedding, also doc-to-vec embedding to build this whole XGBoost tree. So this is the architecture of our deep learning model. Here we utilize a triplet-based Siamese deep neural network. Since it's a triplet model, what we did is like when we construct the training data, we already have the question and the relative answer pairs, and we use them as a positive sample. Also, we randomly generate 15 irrelevant answers for each question and treat it as a negative sample. And then at the modeling part, each question answer is encoded to the same vector space using this encoder. Then we compute a cosine distance between question vector and answer vectors, and then compare in the triplet loss function to penalize irrelevant QA pairs and make sure the question and the relevant answers are close to each other as possible. So this is the details of our encoder. So we follow these steps. When the text comes in, we first do the tokenization, trim the text into words. Then the tokens map to indexes in an embedding layer. So in this embedding layer, we use the pre-trained faster text embedding we download online. And this embedding is trained using Wikipedia and some common corpus data set. And since this fast tag embedding have a lot of parameters, so we don't want this existing embedding to overpower the whole network. So we apply a dropout, a spatial 1D dropout right next to the embedding. And then next, we use LSTM, bidirectional LSTM is type of RNN, to trying to compute the deep complex features for each of the word. And at the pooling layer, instead of using the general global pooling, we find attention-weighted average is a better summarization method here. And at last, the output we get is a final dense vector, which is a deep representation of the regional text. So after we get this encoder, we can encode our existing answers and index them offline. Then at the runtime, at the query time, when a new question comes in, we encode it to the same vector space using this encoder and find nearest neighbors to re-rank the answers. And as a bonus byproduct of the proposed training, since we get this encoder, we can also apply the same workflow to re-rank existing questions. And then what we get is like finding similar question-to-question similarity. So here I'd like to give two examples of the result of our deep neural network. For example, here's a question: can my wife drive on my insurance? And you can see the answer, the first few answers is pretty relevant. And then on the left, you can see this is the similar question we found. And interestingly, without using any single name input or constructing any NER or POS, the deep learning model is able to find the semantic, interesting, similar words. So the questions: can my wife join my insurance? And then find similar question: does my husband have to be on my car insurance? How about my spouse, my girlfriend, even my ex-wife? So it's like it can find very similar questions. And another example is like, is it compulsory to have home insurance? And able to find, is it mandatory to have home insurance? Is it a legal requirement to have home insurance? So it's like when people trying to use this question answering system in real life, they can use all kinds of wording and are still able to find the answer themselves. Here is the evaluation part of this study. Since we want to compare unsupervised method, compare XGBoost, what we did is like we also test the model stability by varying size of the training data. The 100% of training data is about 20K, but we self-sampled at 50% or 10%, and 10% only have about 2,000 question answering pairs. A few conclusions here. You can see the supervised method is overall much better than the unsupervised method. The deep learning model, for the one there's 100% of data used, the deep learning model provides the best results. And then you can see it's like have a big margin compared to just the XGBoost model. Another exercise we did is like we take the output of the deep learning model and use that as one of the input for this XGBoost model. It's kind of doing the ensemble here. We can see one, there's 100% of data, so there's no improvement by doing this ensemble, which is telling us the deep learning model is kind of self-contained, which you don't need to feed in additional NER and a POS and single name, and deep learning can do it well itself. But when we doing sampling the 10% of data, you can see the deep learning model itself is still better than the XGBoost model alone, even there's just 2,000 pairs, which is a little surprising to us because we thought deep learning is pretty need a lot of data. I think part of the reason here is like we use a pre-training embedding, the fuzzy test embedding, and then leverage the existing Wikipedia knowledge there. So if we don't use that, I think for sure we'll need more data. And last conclusion here is like when there's 10% of data, the best model we get is using this ensemble XGBoost plus deep learning, which means when we don't have that enough data, we can borrow the information from NER and POS, those manually extracted NLP features. But it's not recommended because the double the effort of training also increase the running time. All right, so the second case study is about sentiment analysis. This is another project we did at LucyWorks. We got a 50 million product review from Amazon with customer ratings range from 1 to 5 stars. And then we basically perform a 5-class classification. And then we want to compare a deep learning model with a traditional model like logistic regression, random forest, and naive Bayes. So this is the architecture of a deep learning model. You can see it's very similar to the question answering system model. The reason we're still using RNN here is we say LSTM rather than a CNN, because we found like RNN is much easier to tune. It's like just apply a little bit of tuning, the RNN model can be pretty good, and then if you do heavy tuning, it can achieve state of art. But for a CNN model, if you don't tune it carefully, it can provide pretty bad results. So, but stability is pretty important for software building, so here we still use LSTM. And similarly, we use the embedding spatial dropout, but here instead of just using one layer of bidirectional LSTM, we use 2 layers of bidirection to make it more expressive, and then concat them together, and then apply attention layer and then at last get the dense output to predict the sentiment. One extra thing we do is like here we don't just output one thing, so the sentiment is one output. The other output is like we output the attention weights. So if you output the attention weights, a benefit you get is like the attention layer basically telling you why certain words are important for certain prediction. So if you extract the attention weights out and then do some color on top of it, it can show you why this is a bad sentiment. For example, for this sentence, website stock status is not accurate, poor customer service, and then not and poor have higher values here. And then if we do this coloring on top of your UI, you can make the whole thing more explainable, and then people can explore in the UI. Another thing we observe is like the deep learning model is able to capture contextual information pretty well. For example, there's a sentence saying this is awfully good. Even there's a word awful in it. If we say this is awful, then it's a negative. But since awfully is connected with good, so the deep learning model is able to score a pretty high sentiment score. And then another example, the product is okay, overall 5 stars, then it's a positive sentiment. If you just change one word, say the product is okay, overall 2 stars, then the deep learning model is pretty sensitive, and then say this is a negative sentiment. On the evaluation part, we use the same test set from this Amazon review, and you can see the deep learning model win the best traditional machine learning model by a large part. The best model, traditional model, is naive-based. And another thing we test here is since sentiment analysis is a kind of generalizable task, because people use similar kind of sentiment word to describe things, we apply this deep learning model to test the generalization using a different company review data set we download online. And we can see the F1 value is still above 90%. So it's a pretty stable model. And last, quickly, I'd like to show a kind of toy project I did using a Kaggle data set. So this data set is 6,000 cervical cancer images, which labels which belongs to 3 types, and we're trying to predict 3 types of cancers based on the picture people take during the surgery. I roughly did some traditional computer vision methods, basically using the visual bag of words with the sifter features and feeding into SVM. So basically extract the sifter features and use k-means to build the code book, and then build a histogram and feed that image histogram into SVM. And on the deep learning side, since 6,000 image is not enough to build a class, like a whole deep learning network from scratch. So a lot of people borrow the existing trained neural network from WordNet. For example, ResNet 34 is the one I use. I saw people use VGG16. And then what you can do is you utilize this pre-trained convolution layers and then knock off the fully connected layers and replace with your own data set and do transfer learning on your problem at hand. And you can see the deep learning model. Overall, the F1 value is not high because for this data set, even with my own eyes, I cannot tell the difference of those 3 classes. The deep learning model still win the traditional method by a large margin. And based on my observation, it can detect very subtle difference between the pictures. Also, if you apply data augmentation, the F1 can also improve a lot because it can deal with things like rotation better if you apply data augmentation. Okay, we have seen case studies and algorithm comparisons, and you can see based on the case study, the deep learning can easily beat previous state-of-the-art machine learning models. And then it's usually, if you look at the Kaggle winners, they usually use deep learning to win the competition. But we haven't heard there's a large-scale enterprise adaptation of the deep learning that much. I think in summary, there's some issues with deep learning. The first one, there's a huge number of possible settings. If it's a deep neural network, there's all kind of possible architecture you can use. You have to decide the number of layers, the filters, filter size, where to put dropout. And also there's a large number of hyperparameters, the common learning rate, epochs, and mean batch size, and some hyperparameters even have its own hyperparameters. Another issue is that many hyperparameters and methods are actually related. For example, the methods have regularization effect, including convolution, L1, L2, dropout, red loop, batch norm, or stopping. All these can do regularization. So then I don't know if I already apply the dropout or L1, L2 norms, still I need early stopping or not. So the only thing to tell is to experiment and try. There's also the generalization problem. The image deep neural network have been do a good job doing transfer learning, but the transfer learning from NLP is still in the very early stage. Last year there are some publications we try some method. It doesn't really work. But if you borrow the pre-trained convolutional layer in the image problem, it can save a lot of training time, but it's hard to control and understand and easy to overfit too. Also, it's been famous that deep learning is pretty computing resource hungry. So for example, Google claim have an auto ML engine can automatically tune the model for you. But if we train a lot of image from scratch, it may need 800 gigabytes of GPU to run for a week. Unless your company have a big GPU farm, I don't think a small company can do that. Also, the debugging for a deep learning network can take a while, especially given the current packages is not that friendly to use. At last, as a deep learning practitioner, I wish a few areas can be paid more attention to. For example, again, deep learning is data hungry. Most of the winning method in image classification is still supervised learning methods. But labeling a deep learning, labeling an image, even just putting bounding box can be quite laborsome. The autoencoder, and again, is a good start though. But I hope that there can be more unsupervised deep learning research come out. Also, deep learning on small data, how to deal with. Or active learning is like help you choose which example people should label rather than label everything. On the generalization side, a lot of exercises now are people using pre-trained embeddings and initialize the network. But for example, the QA system, we apply the same network on a coding question data set. And we found like half of the word is out of vocabulary because the codes is not capturing in Wikipedia. And how to deal with that kind of problem to map different word spaces. Also, deep learning is famous on image and text data because image, text, and text itself have a lot of structure itself. Although it's called unstructured data because it's from the traditional database domain. And then for the tabular data, how to deal with mixture of different data types, and then how to deal with the explainability for text for the tabular data. It's a big question. So that's why it's kind of rare to see deep learning in some regularized areas such as risk management or clinical trial when the OCC or FDA require the model to be explainable, then nobody uses deep learning. On the package side, as a data scientist, we really like PyTorch because the API is much more friendly than TensorFlow. But our data engineer like TensorFlow because it's easy to parallelize, have low latency, and it has a friendly like Java API for them to use. So I think eventually one of them may win, and then it's easier for us to choose. Sorry for those complaints. So although deep learning is in its early stage and have a different kind of problem, but overall I feel pretty lucky that we are the generation that can witness or even participate in those new breakthroughs. And then we can tell our kids, like, we're the generation that started self-driving car, or things like that. The last page lists some references for beginners. Things, that's how I started deep learning. Any questions?